now let us go to the second part of the carboxylic acid, that is properties of carboxylic acids. Carboxylic acid properties also we can put it in a right way and in a systematical way, that is the studying of the properties of carboxylic acid has got a arithmetic representation, and whenever such a type of the a systematic type of a study, and we can represent as well as we can remember or reproduce the message or the information very quickly. See, all properties can be nicely divided into the following types. In the first type, the hydrogen detachment from the compound, that is specifically the hydrogen comes out as a H plus. So, that H plus giving property is called acidity, right. So, the carboxylic acids will have this particular property as a very prominently and a fundamental property. So, in this we are going to see why it gives the proton, that is called reason for the acidity, and as well as comparison. So, two different carboxylic acids are given, then which is the strong acid, which will be the weak acid, such points can be discussed under this acidity. This is the only one property. And the second property is this is the second property. Under this second property, the OH is going to be replaced, and that is all this called so a carboxylic acid will become into a new group is introduced in the place of OH. Such type of properties are 4 properties are there, that is A, B, C, D. So, 4 properties under this, all these are called acid derivative formation, acid derivative formation. So, acid chloride formation, acid anhydrides, acid esters and acid amides. So, this OH will go new group when enter into the place of that OH, that gives the acid derivative formation. And we have another property, that is only C double bond O will undergo certain reaction, that is called third type of the property, in which you can show that the carbonyl group is totally converted into a CH2 group. It is a reduction reaction. So, reduction of the carbonyl group is the third property. And then there is another property wherein the CO and the O together is lost as a minus of CO2. This is called decarboxylation reaction. This is called as removal of CO2 is known as decarboxylation. So, there are 5 reactions, that is A, B, C, D, E. 5 reactions we are going to see under this decarboxylation. In fact, most of these reactions we have already covered, like Kolbe electrolysis, soda lime decarboxylation, calcium salt pyrolysis and so on. There are 5 different slightly deviated methods of decarboxylation methods are there. We are going to cover that. The lastly, we have one property, that is a 5th property under this the category, that is alkyl group influenced by the COOH. It is not the purely alkyl group, then it is only alkane property, but the alkyl group shows some specific observations because of the presence of COOH influencing the COOH. This alkyl properties are there, that is called alpha halogenation. Only one property is there, alpha halogenation. Under the specific one, we have a HBZ reaction is there. So, this reaction we are going to code under this only one reaction. This is, so here 5 reactions are there, here 1 reaction, here 4 reactions, here 1 reaction. So, total removal of the hydrogen, I will reveal once again, removal of the hydrogen as a plus, H plus, that is proton giving, so acidic property. OH will go and a new group will come, that is called acid derivative formation. The CO and the O together is lost as a CO2, but only CO undergoes reduction. There is also a specific with lithium aluminum hydride. This type of reduction is possible. I will show the mechanism. CO2 removal is called decarboxylation. We have 5 reactions under this category, and alkyl group participating in certain reactions, specifically alpha halogenation, under the name HBZ reaction. We have one reaction here. So totally all these 1, 2, 3, 4, 5 we have a systematically represent, or the student also can conveniently follow the classification as well. The information can be easily, you can have a firm grip over this the classification and the information also. So let us go for the first property, that is acidity. In this, as I said, two the points we are coming. One is a reason for the acidity. Second one is comparison. Comparison of the acidity. Reason, in the reason why after all a carboxylic acid like formic acid should give the proton. Does all the compounds will give the proton? First of all, to give the proton, there should be hydrogen in its molecular formula. But how many compounds? For example, methane is there. Will the methane will give the proton? Never gives, isn't it? Even which has got some similarity with the structure, like I propose a methanol. Will they give the proton? Methanol like this, if it cuts into proton, so what you will get is methoxide anion plus H plus. So let us judge this reaction is got very much similarity, isn't it? The O is pulling the electron cloud, therefore it cuts, and the reaction will become into formate anion formation and the proton. So you can have some similarity here also. O is pulling the electron cloud, because the O is electronegative, it pulls, so the hydrogen is given out. We expect this reaction also very much favorable. But this is also not much favorable, for some extent possible, but not much favorable, because the anion formed is called alkoxide or methoxide. This is called in general alkoxide. The alkoxide anions are destabilized in fact. Why it is destabilized means the O minus is already excess is there. The methyl group, if you arbitrarily if you classify as a plus I group, already excess is there. The plus I supplies much more electron density to the O minus. O minus will become much more problematic. So therefore the system will become destabilized. Whereas here you see, if the proton is given the anion formed, this anion can give the electron like this, the double bond goes the other side. So you will get a beautifully a phenomenon called resonance phenomena comes. The formate anion will become into another formate anion. You can argue what is the major difference. Actually, no much different. This is formate, that is also formate. But the theoretically, as we are aware, that is much know about this resonance phenomena, just like I am carrying a bucket. I just after some time I will change the bucket from this hand to this hand. What makes difference? Not much difference. I am just changing the bucket. I am not leaving any weight, but bucket I am changing from one hand to other hand gives some relaxation or stability. Just like that, the anion, the minus charge from this oxygen gone to that oxygen. That is the problem of this oxygen is shifted to that oxygen. Perhaps again that minus gives back and this gives get back. So these two structures, as you go on exchanging, what happens? This is called the delocalization of the pi bond or the delocalization of the charge. The charge is going on moving. Local means same place, delocal means moving. So the minus charge is moving means the problem is moving. So therefore we get some stability. The problem as such, if it is there constantly, will create the problem. If it is shared by the two corners, naturally stability. Perhaps some more, if systems are there, more resonance structures, that is why gives the more stability. So the formate anion has got resonance stability. Let us equate like this. The formic acid, if it donates a proton, so called formate anion formed has a resonance stability. Therefore the process of donation is easy. Someone can also ask a little critical question, one more. Even the formic acid has a resonance. Where is the resonance eligibility? As such, if you see, you may be not finding the eligibility, because pi bond is there, but there is the other pi bond. it's not necessary 2 pi bonds, 1 pi bond and a pair of electrons on the oxygen is enough to show the resonance. This is called pi p eligibility, right. So, it has a pi p eligibility. So, the lone pair will come, double bond will go. So, therefore, you will get the O minus and the double bond with O and the hydrogen, O will get a plus charge. Okay. This is also resonance in fact. But now the question, if I reframe, why this formic acid gives proton means its anion has a resonance stability, that is why it gives proton. But if I ask question once again, even the formic acid has a resonance stability, why should it give the proton and it shows the resonance? It has previously also resonance is there. But if you fundamentally, if you see that resonance of formic acid, resonance of formate anion, there is a difference. This is the anion becoming into anion, minus to minus. This is a molecule becoming the plus and minus. This is called a charge separation, charge separation. Technically, you can say when a molecule no charge to no charge, you can call it as a best one or the grade 1 resonance. Ion to ion, this is called a charge delocalization. This is called charge separation. This is a grade 2 resonance, this is a grade 3 resonance. What is grade 1? Grade 1 means a benzene molecule, there is no charge and gives this double bond comes here, this will come here, this will come here. So, you will get another benzene like this. This is called the best or the grade 1 type of the resonance. This is called technically no charge resonance. There is no charge either on the structure 1 or on the structure 2. This is the best resonance without any problem. It is going on showing the resonance. Delocalization of the pi bonds will not allow the reagent. That means its life is increased, the stability is increased, the reactivity decreased, its potential energy decreased. That is what resonance stabilization. So, therefore, the benzene type of resonance is the best resonance, that is grade 1. Anion showing is the second grade resonance. The molecule becoming into cation anion, this charge separation is the grade 3, third grade. So, I have a grade 3 right now, which becomes into grade 2 is called upgradation. Grade 3 to grade 2 is upgradation. For this purpose, the formic acid gives proton. If the question is very litigant, what is that? If the formic acid is already having a resonance stability, why should it give the proton and shows the again resonance stability, means that is not that good. This is when compared with this grade 3, grade 2 is better one. So, therefore, for the upgradation purpose, the formic acid gives the proton and becomes into formate anion. That is what the reason we have to. Similarly, we have now a comparison also. A formic acid is having the good resonance, isn't it? Now, let us see a comparison with the phenol. This methoxide is best, it is. If it gives proton, destabilization, therefore, never the methanol gives proton, it is not at all acidic at all. Carboxylic acids are good acids because it is stabilization. Even phenol gives a good resonance stability. Phenol also, if it loses the proton, the anion formed on the phenol gives a very good stabilization. This is called a phenoxide anion. Even this process is ready because the phenoxide anion has got a very good resonance stabilization, and the stabilization number of the structures will be more. See, here formate anion, first one gives second one, again comes back one only, 1, 2, 1, 2, that is all, only 2 structures. But here the structure 1 changes to structure 2, structure 2 changes to structure 3, like that. So, the anion structure will come here, and this, if it is given, this goes to here, one more structure. So, anion structure comes to this side. If 1 is given, this is then goes to the again back to the 1. So, there are 4 resonance structures are there, 1 plus 3, you can write like 1 plus 3. This has got only 1 plus 1. Now, theoretically, if I ask a question, the phenoxide has 1 plus 3 resonance structures, carboxylate anion or formate anion only 1 plus 1, which resonance is better one? Obviously, generally people say that 4 structures are there, therefore, this is the best resonance, but the fact is that is best resonance. The reason is here the O minus is giving electron pair and this is pulling, this is pushing and this is pulling. There is a pull push effect is there in fact. Here this is pushing, but there is no pulling effect because that is giving the double bond polarization. But here it is a self polarization because the CO is a hetero type of bond. If this is giving, this pulls out, so immediately that forms again it is pulling, so it will come. So this is pulling, therefore that comes, that is pulling, therefore this comes. So fast will be there, 2 structures only, but fast resonance will be there. Here 1 plus 3 structures are 1 plus 3, but the resonance will be less when compared with this one. That's why carboxylic acids are stronger acids than the phenols. This is a weak acid. You can see this observation, strong acid and weak acid. You can give a chemical reaction and then verify why this type of the theory is it really sustainable with reference to the practical approach. So, as I am saying is 4 structures should be the more stronger one, but these 4 structures are not which are like this effective structures. So, there are only 2 structures, but the formic acid is strong acid. All carboxylic acids happens to be in general stronger acids than the phenol, because the reason is the phenoxide anion stability is not that stabilized like carboxylic acid formate anion or carboxylate anion stabilization. This you can view. Let us have some more effects on comparison. As we have seen in the amines, for example, if you compare how the aromatic ring influences this one, the ammonia is base. When R with NH2 is there, R is plus I, so the basicity is increased. This is base actually. The R increases. When you have an aromatic system, the lone pair is withdrawn. So, this effect is we are claiming as a minus M influence. The minus M influences, so therefore, it is much more, it is a stronger base, it is a weaker base, right. So, the order you can claim that the RNH2, whenever aliphatic system is there, it will become strong when compared with ammonia. When compared with the weak one, it is really so much of weak whenever aromatic system is attached to the amino, because of the minus M effect influencing, much decreases. Now, the same thing in the formic acid. Formic acid is an acid. If I have an alkyl group attached to the formic acid, what is the influence? It is the plus inductive effect. It is influencing plus inductive effect, therefore, it is decreasing the acidity. So, it is weak acid. And what will be the influence of the benzene on the carboxylic acid? One way, the C double bond O pulls, and this is what happens. So, therefore, this group is called what? Plus M group. If plus I weakens, plus M weakens much more. Should be the weak, very weak acid, isn't it? This is weak acid anyhow, but it should be much more weak acid because it is mesomeric effect, very strong influence. So, the order is expected is this is strong acid, ordinary acid, weak acid, much more weak acid. But in this case, what is happening? The lone pair and the C double bond O shows a resonance like this. There is now this lone pair is in competition. This C double bond O is now have a dilemma whether to use the lone pair or to use the pi bond, which is the more the acceptable, means this is the preferential one. because it is lone pair, it is the bond pair, pi bond, weak bond no doubt, but it is a bond pair. So, this is preferential. Therefore, the resonance always takes place between the C double bond O and the lone pair of the oxygen, but not with this one. So, therefore, this will be always in one plane, that is the carbon, oxygen, oxygen in one plane. The benzene will be in another plane, right. This is in one resonance, aromaticity and all that. Now, if the fundamental is these two planes will be in the same or not? It both will be, can be like this plane and this plane can be like this, or to avoid the steric hindrance, these two planes can be opposite to each other also. In fact, if this resonance is a perfect, when it is a preferential resonance when compared with this one, generally these two would like to be in the same plane, but because this is a preferential one and this is subsided, this resonance between the benzene and the C double bond O will be the second preference, this will be the first preference. Therefore, this will be always in one plane, and this plane is not necessary to be in the same plane because it is not showing. So, it is many times it will be in the opposite plane. So, the plane of the benzene and the plane of the COOH will be in the other plane. Therefore, the plus M effect of the benzene will become null and void. It will not influence the acidity of the proton. That moreover, the resonance goes this side, not to the proton. The anion formed has no resonance stability with the benzene. Be carefully you discuss. No doubt the benzene can show the resonance with the C double bond, but the H plus, if it is removed, anion formed, will it show the resonance with the benzene? No. The resonance with only shows with the C double bond, not with the benzene. So, therefore, acidity is not influenced by the benzene. So, plus M effect will not influence. Then what more can influence means a carbon which is adjacent to this carbonyl group, this carboxylate anion is attached with a carbon here, is attached with a carbon here. This carboxylate anion is attached with the previously with the a hydrogen, in this case an ordinary carbon, in this case it is an sp2 carbon, that is a more electronegative carbon. So, it instead of plus M effect, minus I will be in operation. So, it is withdrawing in fact. So, withdrawing carboxylate anion will be more stable. Therefore, benzoic acid will become a stronger acid than even the formic acid. So, therefore, the order will be like this: benzoic acid is stronger acid than the formic acid. However, formic acid is stronger than all carboxylic acids. In the previous case, you see here aliphatic, ammonia, aromatic, that was the order. Here aromatic is strong acid, then comes the ordinary, this one, then aliphatic acid. So, here specifically what we have to note is benzene plus M effect will not influence the acidity of the carboxylic acid, whereas minus I effect of this carbon, because it is sp2 carbon, will pull. So, therefore, acidity is increased. However, in aliphatic systems, comparison is very easy. In the aliphatic system, we have a comparison that chloroformic acid is stronger one than the formic acid, right? And the formic acid is stronger than the acetic acid, right? This is plus I effect, therefore, decreased effect. Minus I effect, increased effect will be there. And it is acetic acid, chloroacetic acid than the ordinary acetic acid, minus I effect. Fluoroacetic acid and the chloroacetic acid, electronegativity is the criteria. One chloro, one fluoro you can take, this is the strong acid. In this case, this is the strong acid, right? So, the fluoro is stronger one than this one. This is chloro because electronegative group. It is, both are halogens, but the fluorine is the stronger one. 2 chlorines, 1 chlorine, 2 chloro is stronger one. A propanoic acid having the 2 chloro is stronger than the 3 chloro. Both are having the propanoic systems, but the distance factor here, closer the minus I, stronger will be there. And in a system like this, a butanoic acid containing the 4-methyl and 3-methyl. 4-methyl is better one than the 3-methyl. 3-methyl butanoic acid, 4-methyl. Plus I group, closer the one, stronger acid. minus I group away is the more stronger acid. All these effects are on the inductive effect applications will be coming into the comparison, but aromatic carboxylic acids versus aliphatic slight variation is there. Therefore, even the substitutions in amine will have a greater influence on the basicity of the NH2, but the substitutions in the benzene will not are much no much influence on the carboxylic acid, because the plasm effect, the whole plasm effect has become null and void. So, through that plasm effect, influencing factors will be almost negligible. So, let us go for the second reaction, that is acid derivative formation. Acid derivative formation. The carboxylic acid has a OH group. This OH can be suitably substituted with several reagents like PCl5 or PCl3, or you can have a SOCl2, that is called thionyl chloride. Either of the one, not all, can be converted into the acid chlorides. Okay, suitably can be converted. Similarly, when you heat it highly at higher temperatures using some the P2O5, the P2O5 will become into the corresponding phosphoric acid, and the acid will become into anhydride. So, RCO, OCOR, another R will come. So, in the place of OH, Cl comes acid chloride. This is called carboxylic acid chloride. This is acid anhydride. Plus water, that water will be taken by this P2O5, heat it with P2O5. Then similarly, when you add some alcohol and then in presence of acidic medium, best is concentrated H2SO4 and heat it. A few drops needed, but it should be concentrated. Water dilute sulfuric acid will not work, because the removal of the 2 OHs, from this 2 OHs water is detached. So, as the more water in the sulfuric acid, removal of water is not possible. So, therefore, the carboxylic acid and alcohol together, one H2O is removed and the ester will come. This is called acid ester. Esterification reaction taking place. Similarly, when you add ammonia, the moment add ammonia, the acid proton and the ammonia will become NH4 plus, the ammonium salt of the acid will come. But that is not the end reaction, you have to heat it further. Almost a pyrolysis of the salt, removal of the water takes place, that gives into the amide. So, just by adding the ammonia, you won't get the amide. You add ammonia, corresponding ammonium salt of acid is formed. You heat it further so that the water is distilled out, and then comes the amide also distills out. So, acid amide comes. All these four are called acid derivatives. Okay, that is basically the OH group replaced by the Cl, replaced by the OCOR, replaced by OR, replaced by the NH2. All these four are called acid derivatives. In fact, we have a subsequent topic, that is after the carboxylic acid, we have a carboxylic acid derivatives, in which all these four in detail, how they are prepared, under what condition they undergo hydrolysis, what is the relative reactivity, what is the internal conversion factor, and all that we are going to discuss. Right now, just a brief methods of preparations are enough, and the mechanism of esterification in acidic medium, basic medium, reversibility, all these points we will take up under the acid derivative topic. But right now, the carboxylic acid losing the OH, in that place only a new group introduced by with a suitable reagent, that is called acid derivative formation. There are 4 acid derivatives thereby prepared. So, let us go for the third property, that is reduction of a carbonyl group. That is an acetic acid, for example, a general example, let us take acetic acid, when treated with a reagent called lithium aluminum hydride. In this reaction, the CO group, if you find carefully, the CH3 and the O is fine as it is, but this group will become CH2. Is it really, it is 100% true that the CO is converted to CH2 means it may not be there exactly true, because the reduction proceed like this. The lithium aluminum hydride means lithium hydride plus aluminum hydride. In both the cases H is in the form of minus. H minus containing compounds are called hydrides. So, lithium hydride, aluminum hydride mixture I have taken. In fact, this exists as a lithium plus 1 and aluminum with minus in the coordinate complex, like also you can show, nothing wrong. Now, here the lithium hydride is relatively more reactive than the aluminum hydride. Therefore, let us have a reaction with this, not this aluminum hydride, you preserve it. So, H minus is added on the carbon, lithium is added on the O. It is an addition reaction taking place. So, therefore, lithium O will become O minus with the lithium addition plus. So, this side O on the carbon H minus is added, there is a OH comes. Just like a carbon with 2 OHs is unstable, that is the general principle in the organic chemistry. Whenever a carbon has 2, phosphorus and boron and silicon, so many compounds exist 2 OHs on the same element, but in the carbon the 2 electrons will come like this and the OH and the H will eliminate as a water and it will become a carbonyl group. That is what in the carbonyl chapter also we have seen. A carbonyl compound, if you add HOH, it gives a diols and they will become immediately loss of water, it becomes back into the carbonyl group. So, the carbonyl group, if you add water you will get this one, remove water, minus of H2O generates the back reaction. So, whenever 2 OHs are there, similar to this one, there is another concept. Instead of 2 OHs, if 1 OH another Cl is there, so same reaction, that is the lone pair will come, Cl will go. In fact, outgoing property of the Cl is much more better, isn't it? So, therefore, and this which undergoes formation of C double bond O easy, means this is more easy. Here the removal is HCl minus. Similar the way O minus and OH. Here the O minus coming here and OH. This is also more easy. So, this is OH and the lone pair becomes double bond, OH will. Like that here also there is a O minus attached with OH. Will it sustain? No. Immediately the O minus becomes double bond, this OH will go. So, what comes is CH3, C double bond OH. This is a well known compound, acetaldehyde. So, therefore, acetic acid in the first step of addition of lithium hydride, it will become acetaldehyde. Acetaldehyde, the C double bond O is more reactive towards nucleophilic addition than a resonance stabilized C double bond O. So, therefore, one more lithium hydride will be added. This mechanism I am explaining, in fact, lithium hydride. So, again H minus will be added, lithium will be added. So, therefore, you will get finally CH3C, O with minus and a lithium salt plus 2 H minuses are added. So, this is actually the last salt, but here lithium salts that is ethoxide, lithium ethoxide is very highly hygroscopic and hydrolyzable with the moisture available in the air itself. So, therefore, from here to here you need not to add separate water and do this reaction. This is not necessary. Even with moisture also, it seems the lithium salts undergo slowly hydrolyzes to give the alcohol. That is why after adding the lithium aluminum hydride as a step 1 and the step 2 add water, this is not necessary, it seems. That is why only lithium aluminum hydride you get the alcohol, that is what telling. So, it is the reaction as such. If you see, the OH is intact, and the CO is totally reduced. Is it possible? Means not like that actually. The C double bond O is only undergoing partial reduction to become into the alcohol type, and that eliminates water. This OH is not intact, this OH is going out. If it is really labeled, that goes out as a water, isn't it? So, this OH goes, an aldehyde is formed, undergoes further reduction to give the 1 degree alcohol. So, the carboxylic acid on reduction gives this reaction. In fact, you can also have an additional point here. Instead of the OH, see in this what is outgoing OH? If Cl is there, what happens? Cl goes much more better than the OH. Therefore, instead of the carboxylic acid, let us have a acid chloride. Acid chloride. As lithium aluminum hydride, what happens? First step, lithium hydride is added. Similar way, Cl goes immediately. So, acetaldehyde forms from the acid chloride much more easily. So, therefore, acid chlorides, acid anhydrides, OCOR goes in the case of OH or OC. In the case of ester, OR will go. All this will go one after the one in the similar way, all will lead to give the alcohols, except in the case of amide. If RCO NH2 is there, NH2 will not go out because the ammonia is strong base, outgoing is weak. So, therefore, NH2 will not go, it gives 1 degree amine. So, therefore, you can make a general statement, acids and all the acid derivatives except acid amide on reduction with lithium aluminum will give the same product, that is alcohol, right? That is 1 degree alcohols, because in all the case mechanism is same, only outgoing group is differs. In the alcohol, it is in the carboxylic acid, OH will go, in acid chloride, Cl will go, aldehyde will be formed, again reduction gives the 1 degree alcohol. Therefore, acids and acid derivatives except acid amides will give the 1 degree alcohols in reduction with this lithium aluminum hydride. This is the third type of the reaction. Let us go for the fourth type of the reaction. In the fourth type of reaction, I said CO2 removal, that is in the carboxylic acid COOH. If the CO and O together is removed, then it is called minus of CO2, known as decarboxylation. Under what factors this decarboxylation will become easy? After the general decarboxylation, we will also takes place if some substitutions are there in the alkyl group, what influence will be there on the decarboxylation also we will discuss. First of all, let us see general discussion type of decarboxylation. One is soda lime decarboxylation. Soda lime decarboxylation means a carboxylic acid, when I add a sodium hydroxide and the calcium oxide, this mixture is called soda lime. The soda lime, when it is added, first the carboxylic acid turns up into its salt, O minus Na plus, salt formation, obviously because of the base is there. Then what happens, the O minus will come and these 2 electrons will be given out and this will become into it passes through the R minus, in fact, right. So, the CO2 will be removed and then R minus will take back and you will get the RH is formed. So, you will get a loss of CO2. It passes through carboxylate anion as an intermediate. So, one can guess what type of group will make this decarboxylation easy? The group which stabilizes the carbanion. That means some withdrawing groups, if it is there, it becomes easy. So, it is also observed that a chloro group and a methyl group which undergoes. So, naturally the chloro anion stabilizes. So, all that questions also can be asked. So, it passes through this soda lime, a strong base, CO2 is an acid, that acid is taken away. Finally, actually the CO2 you do not get, but in the form of its salt, sodium carbonate will be the one of the byproduct will be there, alkanes preparations, it is the one of the method. The second one, let us take instead of soda lime, we have a Kolbe electrolysis. In this Kolbe electrolysis also, RCOO-Na will be taken, a salt is taken and dissolved in the water, aqueous solution you take, that means in presence of water, electrolyze it. When you electrolyze it, anion goes to the anode and undergoes a loss of electrons, right. So, this is anion goes a loss of electrons. So, it will become into the RCOO minus will become into dot first. So, anion becoming into dot means loss of electrons, this is called oxidation. So, at anode, anion goes where? At anode. So, therefore, at anode oxidation, minus of electrons is oxidation. At anode oxidation taking place, anion will become into free radical. The free radical undergoes a breakage into dot dot. So, this electron will become this one, it passes through the free radical then. Okay. So, Kolbe electrolysis passes through the free radical. Once again, which type of the compounds undergo Kolbe electrolysis fast means all the groups which stabilizes the free radical. That means must be the 3 degree, 2 degree, 1 degree will be the order, because the carbanion is different. Carbocation and free radicals are different, exactly reverse will be the phenomenon. So, this now later will become into the CO2 is formed. So, at anode CO2 will be formed, R and R will be merged up with another R dot and you will get the RR. So, these two products will be at anode, carbon dioxide and the two R's formation. Rather now the cation Na plus should undergo reduction, but it undergoes refuse. So, instead the water will take the electron, this is called at cathode. At cathode electrons are accepted, water will become into H plus and the OH minus. The H plus will take the electron, will become into H dot. That H dot will join up, you will get the H2. However, the Na plus and OH minus forms into NaOH. So, these are the 4 products, 2 are formed at cathode, 2 are formed at anode products. Therefore, there are some questions are coming, divide the products, there are 4 products formed, divide the products into cathode products and the anode products. The anion loss of electrons free radical, the free radical turns up into CO2 and RR. It is very clear which 2 are anode products and which 2 are cathode products, no need to by heart, just apply the analogy or the logical approach, analytical way. If you think anion undergoes, anion goes to anode, anode de-electronation is oxidation. So, at anode reduction takes place, wrong, at anode oxidation takes place. The anion becomes into free radical, the free radical becomes into the alkyl free radical and the CO2 neutral molecule will be given out. That is what in the electrolysis compartment, if you add one phenolphthalein, at anode CO2 is released, CO2 is acidic. So, therefore, at anode the decolorization taking place, at cathode Na and OH, accumulation of NaOH, basic medium. So, the pH increases, therefore, if you add a drop of phenolphthalein to this electrolysis medium, at a cathode the pink color develops, at anode decolorization, that is no color you find. So, that is what also a progress of the Kolbe electrolysis one can observe. At a cathode Na and OH accumulates, therefore, these two will develop the basic medium and the solution turns into the pink color. So, finally, the 4 products are formed. So, the RCOONA, 2 RCONA you have to take, 2 CO2 are formed, 2 R's will join up into RR. So, minus 1 carbon, double it and the corresponding type of the problems can be worked out. This is second type of the decarboxylation, in which sodium salts acids not actually acceptable, sodium or potassium salts electrolytes, isn't it? In the form of solution you have to take and electrolyze it, the reaction proceed like this. The another type of the decarboxylation is calcium salts decarboxylation. Calcium salts of undergoing the pyrolysis. Here you take any carboxylic acid, calcium salt, you can represent like this also, nothing wrong, RCOO with a calcium salt. It is solid. So, take this solid, go on heat it, do not put any reagent. This is called a Merry heating, right. In the Merry heating, what is happening is calcium carbonate will go out as a substance, and what comes out as a distillate means RCOOR will have a low boiling point, will come out as a ketone. And the calcium carbonate will be in the flask, it is left over. This will be the distillate, it will come out as a vapor and you cool it and you will get the solution as if it is distilled over. So, the calcium salts of any carboxylic acid and 1 COO plus O with calcium carbonate is formed, and that and this will be joined as a ketone. So, the ketone you observe carefully, it is a symmetric ketone, right, provided if you take a symmetric type of carboxylate, that is calcium salt, both acids will be identical, then 2 R's will be identical. A symmetrical type of ketone will be formed and it will be a preparation for the ketones. Instead, you have another method, calcium salts only, but you take the calcium formate also with it, calcium formate also mix and then distill it. In this distillation, what happens? The corresponding acid is converted to aldehyde. If 2 R's are there, 2 aldehydes are formed. This works as a reducing agent. Calcium formate acts as a reducing agent. Both acids are giving with no loss, no gain on basis. Here, if 4 plus 1, 5 carbons are the 4 plus 1, 5 carbon aldehyde will be coming. 2 moles of calcium carbonate will be identified as a residue. In the residue, you find for every mole of this one, every mole of calcium carbonate is consumed, 2 moles of calcium carbonate will be observed. You too can have only calcium formate. For example, calcium formate alone is taken, then what? Without any this one. Calcium formate alone if you find, then also calcium carbonate is formed, formaldehyde will come. You can note this point also. Alone calcium formate, if it is distilled, just a pyrolysis, you can call it as a pyrolysis, or you can call it as a distillation. Salt, all these are all solids. Solids distillation means you go on, heat it, first they melt, they become liquid, isn't it? Then they start boiling and then undergoes this type of the breakage reaction. Lower boiling point compounds will be distilled out and the higher boiling point salts will be recovered in the flask. They will be in the flask, but this comes out as a volatile compound. So, calcium formate alone if you take, you will get formaldehyde. Calcium, any other salt you take, you get ketones. Calcium salts plus calcium formate mixture, this is specifically mixture. Whenever you take mixture of calcium salt with calcium formate, then aldehydes are formed, corresponding aldehydes will come, right. Then lastly, you have one more type, a carboxylic acid with silver salt. Silver salt have got some specific observation. Here the bond will be somewhat covalent bond will be there. So, therefore, all the salts of calcium and sodium are highly soluble in water. Benzoic acid, if it is not soluble in cold water, its sodium and calcium are highly soluble. But whereas silver salt, because of the covalent bond nature, they get as a precipitate. So, you take the silver salt of the carboxylic acid, add a bromine and then heat it. Here the bromine and the silver becomes into silver bromide, okay, and then this RCOO, CO2 will be removed, R and Br will become into RBr. Here also anion will become into the first free radical and then CO2 removal, R dot will come, passes through free radical mechanism and then carbon dioxide will be observed here. Decarboxylation, directly carbon dioxide will come, a silver bromide and alkyl bromide, decarboxylation come bromination, both are taking place. This is a name reaction called a Huns-Decker reaction. Huns-Decker reaction, name reaction this is. Pyrolysis has no name, but the Kolbe electrolysis is a Kolbe electrolysis. First one, soda lime decarboxylate, has no name. This is Huns-Decker reaction, calcium. In the calcium salts, we have some, instead of calcium, barium and thorium if it is taken, some names are there, but this Huns-Decker reaction is very popular. Silver salts of the carboxylic acid, when heated with bromine, not chlorine, only bromine allowed, and again silver salts only taken, then corresponding the alkyl bromide, decarboxylation come bromination will be the reaction, that is called Hunt's Decker reaction. In all these reactions, decarboxylation is taking place, right. One point you can emphasize, a decarboxylation is a process of right. This is a carbox, that is carbanion will be formed, CO2 will be released. So, it passes through the carbanion. So, what type of group means on this system, if you have a withdrawing group, then the carbanions are stabilized, the reaction will be taking more facile. All electron withdrawing groups will promote this decarboxylation, a general statement. So, in this system, for example, if you have a carboxylic acid having a carbonyl group on the alpha carbon, beta carbon, right, on the gamma carbon and so on in different places, let us put the carbonyl group. The carbonyl group is obviously an electron withdrawing group. Okay, this group we can call it as a minus electron withdrawing group, pulling group, isn't it? So, where should be it should be the means obviously on the carbanion, if you have a C double bond, it is not benefitable. So, therefore, this will be the out of the picture. If out of the next if the anion comes here, which will be better stabilizes, means the anion, if it comes here, I think it is better stabilizing, isn't it? But this is called what, with reference to the carboxylic acid, the alpha beta, isn't it? So, the beta carboxylic acid will be the more stabilizing with this anion. So, beta keto acids will be more favorable for the decarboxylation. This is one fact. Why means the CO2 removal makes the anion. So, the carbonyl group should be on the next carbon, not on the same carbon. On the next carbon, if it is there, the minus comes and shows resonance. This is one reason. There is one more reason is also a beta carbon. This is CO, isn't it? So, if COOH is there, so with reference to the carboxylic acid carbon, this is alpha carbon, beta carbon. On the beta carbon, if a carbonyl group is there, see this hydrogen will be already with this CO group in hydrogen bonding. There is a beautiful 6-membered ring is there already, isn't it? Now, this decarboxylation means what? The hydrogen will be cut here, the 2 electrons will be coming here, right? And these 2 electrons will be coming here, and these 2 electrons will go in fact and make this temporary bond to become permanent for some extent. Then the next structure will be like this: RCO with hydrogen, a double bond with the carbon with the 2 hydrogens. Okay. Then the CO2 you have to write as a totally detached molecule. So, the intermediate of this ene with OH, it's called enol. So, this enol has got now impact in this particular decarboxylation. Because of that, the 6-membered ring formation, the hydrogen, actually this hydrogen should come to this carbon, but it passes through the enol and then tautomerizes to this carbon. See the double bond, that is 2 electrons will come, this will go here, it will become minus and H jumps here, nothing but the tautomerism. So, therefore, through the tautomerism you cannot write resonance symbol. Tautomerism is 2 different compounds which are in equilibrium. So, it will become a keto. That hydrogen has come here. So, beta keto acids undergoes a favorable decarboxylation because of the 2 reasons. One reason is if you remove CO2, anion comes which can get resonance stabilized with the beta keto. If the keto is there on the same carbon, anion and how they get, they cannot, they are not eligible to show resonance also. Anion and the double bond on the same carbon, no. Anion and double bond alternative carbons, it is a pi charge conjugation, resonance stability comes. So, therefore, beta. If next carbon also it will work as a minus I, but not resonance will not be shown. If minus comes here, pi bond is here, minus is here, 2 single bonds in between, no resonance. So, therefore, so gamma is also not suitable. Beta is suitable because of the 2 reasons. First reason is resonance stability. Second one is through this 6-membered ring, a enol is formed. The enol later tautomerizes to become the ketone. So, therefore, a ketone and a CO2 is formed readily from a beta keto acids. So, whenever a beta keto acid is there, just heat it. No need to so called that is calcium salt or the sodium, that is soda lime, all such things not necessary at all. Just heat it. That is all. Decarboxylation takes place and this will become ketone, that will become into CO2. Why this decarboxylation is so easy means this particular mechanism is explained. In fact, it was asked in one IIT examination also. Show how the beta keto acids undergo favorable decarboxylation, explain the phenomena and so on was there. So, this is what the secret of that, why the beta keto acids undergo favorable decarboxylation than even a alpha, because the point I said the minus I group should be very close so that decarb, but very close is not working here, because this 6-membered ring, to accommodate that 6-membered ring, the carbonyl should be not on the alpha but on the beta. Alpha is not useful, beta is useful. So, beta keto acids undergo favorable decarboxylation. So, the last reaction of the carboxylic acid is a alpha halogenation. In the alpha halogenation, the R is undergoing to influenciation by this carbonyl group. There is some reaction taking place in the R influenced by the COOH group. As we have seen in the aldehydes and ketone, that the acetaldehyde undergo very favorable halogenation. See, acetaldehyde is a liquid, right? You take the chlorine gas, pass this gas into this one, obviously all the halogens one after the one however get halogenated, and this is one of the very favorable reaction in the carbonyl compounds. And the explanation is given why the hydrogens are very much reactive towards halogenation, means they show hyperconjugation followed by the tautomerization, right. Hyperconjugation means resonance, you can show like this. This show hyperconjugation means resonance symbol you have to show, that is O will become minus and the hydrogen is cut and shown there only. This is called what? Hyperconjugation, right. If the H plus goes there, then it is called the tautomerization. In the tautomerization, the double bond O will become OH, right. So, this type of tautomerization is possible through the hyperconjugation. That is why the hydrogens are said to be attached for some time, detached for some time. They are in equilibrium, okay, fast exchange will be taking place. Therefore, these hydrogens are very much reactive. So, therefore, if you add chlorine, then immediate reaction takes place. So, this is what called alpha halogenation, which is actually promoted by a drop of base also, because in basic medium enols are more stabilized. Therefore, a drop of sodium hydroxide if you add, the reaction will become very highly much more reactive. A drop of acid will have some problem of this halogenation, okay. However, now you just compare the same reaction with the carboxylic acid, that is an acetic acid, let us have a very much closer similarity. There is also hydrogen. Can this show the hyperconjugation? Means yes, it shows hyperconjugation. Therefore, we expect the same reaction. You pass the chlorine gas into the liquid of acetic acid, no reaction. There is no reaction. Similar reaction, this is liquid, chlorine gas, no heating there, no heating here also, but no reaction. Because the hyperconjugable hydrogen is want to show the hyperconjugation in fact, but the lone pair on the O is want to show the mesomeric effect. So, the plus hyperconjugation is in competition with the plus mesomeric effect. Out of these two, which is more favorable, means this is a resonance, this is a no bond resonance, isn't it? So, therefore, always a mesomeric effect dominates over the hyperconjugation. So, that is why the hyperconjugation is in fact suppressed. Though hyperconjugable hydrogens are there, their effect will be less. The mesomeric effect always dominating. So, the reaction will not take place. But I want a alpha chloroacetic acid, so that I can do alpha amino acid, which is a starting material for the proteins and all that. Therefore, the reaction is very sensitive and important reaction for me. Somehow I want to get it, but the reaction not taking place. This was achieved by the three scientists called Volhard, Jelinski. Three scientists together find out that only chlorine will not work out, but in presence of chlorine, that is take chlorine in presence of in fact the phosphorus, this reagent will enough to promote this reaction, you will get a alpha chloroacetic acid formation. What is the further application of that? You add ammonia, you will get amino acetic acid, that is glycine will be prepared. All the corresponding carboxylic acids can be alpha chlorinated using this particular reagent, chlorine phosphorus. The reaction is known as Hell-Volhard-Jelinski reaction. In this reaction, P and Cl2 will be reacting and giving the PX3 or PX5 type of compounds, in which equilibrium maintains, maybe reactive intermediates of chlorine may be influencing the reaction. Therefore, alpha halogenation, which was not possible directly with ordinary chlorine, made reaction easy with adding the presence of this phosphorus, makes the reaction. This is called what? A slightly improved reaction. It is nothing but the alpha halogenation. So, this reaction is called Hell-Volhard reaction. A suitable question is, for example, if I take a butanoic acid, if I treat it with chlorine phosphorus and subject it to one particular condition, what is that? Monochlorination. Monochlorination, what is the major product formed? It's a very suitable question. Now, the chlorine I can introduce here, that is 4-chloro-butanoic acid, 3-chloro-butanoic acid, 2-chloro-butanoic acid. You too can get one more product also, wherein this OH also can be replaced. So, I have now the 4 products. So, any one of this group, 4-chloro-butanoic acid, 3-chloro, 2-chloro or butanoyl chloride may be written. After that, which will be the major means, this is the right answer, that is 2-chloro-butanoic acid is the right answer. This is the right term, because these hydrogens are in hyperconjugation. So, therefore, the reaction taking place at the second one, though I denied that the hyperconjugation is suppressed by the mesomeric effect, but still the reaction takes place at hyperconjugable hydrogens are preferable over normal hydrogen. Therefore, alpha halogenation was promoted, however, by the presence of the phosphorus, which is specifically said as a HVZ reaction, very popular reaction used for the preparation of the amino acid, that is alpha amino acids preparation. This alpha chloroacid will become later into alpha amino acid that creates the protein's history and so on. So, therefore, this is the last reaction, that is carboxylic acids undergo halogenation. Specifically, this particular reaction is known as HVZ reaction.